however I can. So my background a little bit is I've been doing this since basically I've been in diapers, and grew up as a tech level with my parents and actually ran a service company for a while. I've worked with industrial refrigeration companies, major OEMs, R&D laboratories, universities, etc. And now I'm doing something really cool with CO2 heat pumps that I want to tell you about today, and what the promise of the technology holds and how we can work to apply it. So at any time, if there's questions, please put them in the chat and we'll see if we can address them as we can, or hands up. It's a lot more fun for everybody when we're interactive on these things. So please chime in. So first, I want to start with a question. This is one that most people in this room may know, but it's always perplexed me, is that 40% of all greenhouse gas emissions come from our buildings. And it doesn't always seem like that, but it is really interesting because we can actually do something about that. So if you look at the way the systems break down over time, or the way the CO2 emissions break down, roughly 27% there on the right, 6% and 7%. So it goes into the construction, the building, and so on. But the really interesting thing to me is that now that we have renewables and the energy grid is starting to make a real go at reducing their carbon footprint, you can see in the bottom left chart there that the electric power is down 26% since 2005. But unfortunately, our buildings are not. They've been holding strong and steady right at the levels they've been for the last 15 years. And so these are studies coming out of The Economist and so on. But we're expected to continue building more buildings. It's going to increase to 2030, and then it's going to double the 2030 numbers again. So we really should start paying attention to this, and our codes and regulations are catching up. And so if we look at how this breaks down, this is a report from ASHRAE. It's their position piece on building decarbonization. And buildings and their metric account for 37% of global CO2 emission, or global greenhouse gas emissions. 46% are in the residential, 27% are in the commercial. But then there's this big chunk of embodied construction materials. So in these categories, we have things like chillers, air conditioners, furnaces, heat pumps, hot water boilers, domestic hot water. And those are where me and my team have really spent a lot of time focusing and realizing that we can make a huge difference. Being an engineer and being as nerdy as I really am, I love to drive down and figure out where those avenues to do something about these numbers really come into play. So with that, you look at those pieces of equipment, they're dirty and they're basically toxic. So greenhouse gas emissions come from fossil fuels, electric resistance heating, which isn't very efficient, and it takes a lot of power generated by dirty power stations. So if we eliminate those first two, which codes are doing today, we are left with heat pumps and chillers. And at that point, we're starting to talk about high GWP refrigerants. Take, for instance, a 410A heat pump. Let's assume it has about 3 pounds per ton, which is about the average of almost any equipment out there. And we have a 500-ton load, which is pretty representative of a lot of mid-sized commercial buildings. The EPA estimates that we have 20% leakage of that refrigerant every year, and it has a high global warming potential of 2,256, 200 times worse than CO2. And let's say it has a 20-year life of that equipment. That's being generous for some systems, and it's being conservative for others, so it's an average. Do all the math, that adds up to 338 equivalent tons of CO2 emissions a year per building. Or I like to equate it to like how much pollution is coming out of the back end of a combustion vehicle. That's 73 cars. Add that up for the life of a building. That's a significant amount we're not even addressing today. And that's just the refrigerant. That's not even getting into what we like to do as energy engineers and dialing all our systems in. So there's a huge opportunity here. The other part about this is these refrigerants that we're using in our heat pumps are frankly toxic. Synthetic refrigerants like HFCs, HFOs that are coming out now have have a compound called PFAS, or another name would be forever chemicals. These are chemicals that do not break down naturally or take a really, really, really long time to break down naturally. They've been linked to tremendous health issues throughout Europe. And even just last week, the European Parliament has passed legislation actually phasing these things out before we even start with them here in the United States. So the EPA classifies these forever chemicals, the per and polyfluoroalkylide substances, as widely used, long-lasting chemicals that break down slowly over time. They are in 410A refrigerants, 454B, the alternate to 410A, 134A, which we use in our chillers, and the new HFOs like 1234YF used in your car. These things break down and immediately go into the water supplies, which affect human health. There's a lot of studies out of Germany and Norway and Denmark. And as I mentioned, the EU is banning these things out. So by 2026 and 2028, they're not allowed to be used in air conditioning equipment anymore. And the EPA has committed to doing this by next year, putting together a roadmap, and they issued guidance on testing already. So it's coming, even though most of us have never heard about it, it's definitely coming. But I'd like to say that the world is changing. Here in Washington State, where we're all sitting today, or even in the Pacific Northwest as a whole, new regulations are coming online all the time. The Washington State Department of Ecology is issuing guidance on HFC bans coming forward. Basically, anything over a GWP of 750 is squarely targeted at the beginning of 2024. And they have about a 5-year run up, and they want to start bringing that down to less than a GWP of 150. That means we're going to have a huge refrigerant change on our hands. California is already there, and they're about 6 months to a year ahead of Washington State at the moment. New York's getting there, Toronto, Ontario, and even the states that don't have anything, they do have climate action plans in place and legislation happening. So our rules and regulations are saying no more natural gas furnaces and boilers. They're trying to restrict the use of electric resistance heating in boilers. So what are you left with? We got heat pumps, and now we got to do something with them. So I'm going to make the argument that CO2 heat pumps are the absolute best way that we could possibly go with this policy. They are 100% fully electric, meaning we don't have to burn fossil fuels. I put a caveat there on fossil fuels because they still exist on the power grid. We have hydroelectric power here in Washington State, which is not the luxury that a lot of people have around the country. But if you get over about 2.5 times more efficient or 3 times more efficient on the electric, you are still a net neutral on your energy bill at the end of the day. So that 3x is really important to get above, let's say, an 80% furnace. You need to get to 2.5 COPs, 250%. So next, it's regulation proof. It is the only refrigerant out there that is capable of not being regulated out because it is the baseline all others are judged against. And I'll show you a few things with that coming up here. It's very ESG friendly for those who are into that thing. It's, if you want to get into that, please give me comments. It has a GWP of 1, meaning it is the baseline. All others are judged to it. 1 equals carbon neutral. ODP, so ozone depletion potential. It's very important to keep the Montreal Protocol spirit alive and keep our ozone layer from deteriorating. So we have to maintain that. And then in application, it's one of the safest refrigerants out there. It's non-toxic and non-flammable, which can't be said for many other refrigerants, especially the new ones. It's efficient. It's one of the most efficient heat transfer fluids there is. There was once a study done by the Oak Ridge National Labs. They ran through all the supercomputing that they could do, every chemical composition. And at the end of the day, they came up with, you should use CO2, propane, or ammonia. Those are the limits, and they are the best. All others should be judged against them. And that stuck with me, and that's where it got me going on the CO2 heat pumps. And they're fantastic over a huge operational range, and they're great for chillers, hot water boilers, and domestic water heaters, as well as comfort cooling and going toe to toe with other technologies. So with all this information, me and my friends have been talking about this for years and years and years. My first CO2 system went into California back in 12 years ago now, and it's still running and doing great. So our CEO has worked with a CO2 service company for a number of years prior to doing this, and nobody was putting together a CO2 heat pump system made for North America. So that's where we got involved. We're like, we are putting our hands up and we're going to do it. It's not something that's new and unnatural, but our purpose is to create a decarbonized and detoxified option for our built environments, eliminate the need for fossil fuels, and utilize these clean electric CO2 heat pumps. So I wanted to show you a little bit about our products first, and then I'm going to get back into what makes a good heat pump and why we should care. So first of all, these are the products that my company has been putting together. We have standardized and modularized heat pumps and gas coolers for the market that can go up to 180-degree hot water and down to 30-degree supply cold water, all in the same machine. Think of this as a central plant in a box for small-scale commercial projects, where you can combine your domestic hot water, your heating, and your cooling all together. And we put it all together in a nice cost-effective point. So our primary goal was to decarbonize and create net carbon neutral products. But there's a couple important milestones where this is hard to do. First one is it has to be based on existing components and technologies. We have found products that are in distribution, set up with a long track record, especially in Europe, Africa, and Australia, where they have almost 80,000 installations of transcritical CO2 systems working today. But surprisingly, very few actually exist in this continent. And so we're aiming to change that. We need to make it economically viable across the board, because nobody wants to pay more for something that they already have and they have access to. And I think we've accomplished this here. It's designed for the application intent. A lot of heat pumps today can't go above 120, 135 degrees, absolute maximum, versus our boilers are set up for 180, 160 to 180 degrees. What are you going to do? Are you going to rip out every single piece of terminal equipment, change all your piping, 200 plus VAVs in a building, and in a finished building? No, that's a nightmare. And that's why the adoption's been so slow. If you can do it with a like for like replacement, now you really have something. We're aiming for the highest overall efficiency. Seattle and Washington State have some of the highest overall energy code requirements in the country. And if you can pass here, you can pass most anywhere. And through all this, we discovered a few really novel approaches to make it all work. And we have some patents on the whole process and a lot of proprietary information that went into designing controls and algorithms. And we partnered with the best in the world to do that. So I want to emphasize that this is mature technology. We've partnered with a company primarily to do a lot of the mechanical systems out of South Africa. They have done over 300 projects of the transcritical nature for industrial and supermarket applications. They grew up working in the mining, mission critical, cannot fail your life safety world. And so these things are bulletproof and rock solid. They have lifetime expectancies of 20 to 30 years easily, some over 40 years on their systems. There's a lot of scrolls today. Mine only last 7 years, let's say, and you cut it out, throw it away. These ones are actually serviceable, reciprocating engines like you would run in your car, but they're actually doing refrigeration, which is so cool. And adding a few extra touches to polish it off to make it suitable for boiler operations and the loads that we have here, we have a really amazing product that we can push forward. So now I'm going to take a step back. That's what we do, but I'm going to take a step back for anybody and say, what makes a great heat pump, especially one for our day and age where we have these intense regulations. We have this new knowledge of toxic and unhealthy refrigerants and industrial chemicals, and we want to get rid of them. So always our first question is it code compliant? So there's really high GWP restrictions now, or really low, I should say. and there's COP requirements for energy codes. Next, we want to make sure safety is absolute paramount for both ourselves, our techs, our building owners, and anybody else who might be near this thing. So we want to be recipients downstream of this, really. And so we want to make sure that there aren't any of those concerns. And next, we really have to make sure it meets the application. Can it meet the temperature requirements? Can it meet the flow rate requirements? Are we going to have enough power to do electric heat? Those all really come into play, especially in cold climates. Now we start talking about defrost potential. And so I'm going to put a chart up here with too much information on it, in my mind, but it really helps you get a lay of the land on how all this works. So these are all the refrigerants that are basically possible for heat pumps today that are being explored and wanting to be put into commercial products. We luckily had the ability to use 410A and 134A refrigerant for a number of years. That was our last big refrigerant transition point 20 years ago. But unfortunately, we're getting to a point where we have to change refrigerants again. And we don't want to have to do it a third time after this. And so you look at the end goal. What are our targets? What are the regulations? Why is everybody going to this? So the first one and foremost is GWP, global warming potential. Right now in 2024, GWP of less than 750 is going into widespread effect. Next, within 5 years after that, GWP of less than 150 is going to be coming in strong and hard. So that is a first real metric to keep that refrigerants under control. Next is just the legacy ODP requirements. Honestly, trying to find a synthetic refrigerant that can do a 0 ODP is really, really hard. And if you look on the far right, that 1233ZD, which a lot of people are touting as a great refrigerant, even though it's a small ODP, it has an ODP. A lot of people round it off to 2 significant digits just so you don't have to see the last bit there. But that's really important. Next, it's safety class. So safety class is really interesting. So that's non-flammable and non-toxic as a class A1. So you won't burn, you won't explode, and it won't make your lungs burn and kill you. So there are other options. 410A and 134A are great, safe refrigerants. But now you start looking at the other natural refrigerants, such as propane and ammonia, going across the right, R290 and R717. Though propane's explosive, meaning it will combust and explode. And ammonia is both mildly flammable, but also highly toxic. So there's challenges with both of those. And the new refrigerants that we're trying to get into, these HFOs and the alternate HFCs, they are all mildly flammable. So now we have to do special regulations and reporting and different safety mitigation techniques to make it all work. And the last one that's really come into play in the last 6 months to a year is this PFAS requirement. And Europe's already fully acted on that, and the EPA is going to come down hard on it next year. So look across the right there at all these charts. Each one of these refrigerants has some kind of issue except for CO2, which makes it one of the absolute best things to use. Unfortunate one is R32, which a lot of people thought was going to be the solution. I have it highlighted in yellow there for a reason. The current classification of R32's GWP is 677. But as of 2 months ago, the IPCC regulations AR6 or 6th edition has pushed it up to a 771, which unfortunately is over that threshold. I'm sure there's going to be a lot of pushback on that recalibration, but it puts it in that hazardous territory on regulations that may or may not be able to be used. Add up all the potential that you can do it with some of the geeky details, like how low a suction you can go, how high a suction you can go. And CO2 is really the only answer. The real big trick about it is it operates transcritically to make it happen, which is new technology. So just for the sake of illustration, I don't know how many people understand refrigeration cycles that well, but we look at subcritical versus a transcritical refrigeration. We see this little loop here across the top. That's a pressure, and this is a pressure enthalpy chart. So that's the vapor dome. Below that dome, it's liquid. Above that dome, it's vapor. Far left side, we got liquid. Up above and top right, we have supercritical fluids. Now, every standard HFC, HFO system is a condensing system where we always have to get beyond and inside that vapor dome. A transcritical system says, now we don't really care about that anymore. And we push the pressure up as high as we can. And now we have that entire top line to draw heat off of. Our capacity is directly proportional to the difference in enthalpy. So the more difference in enthalpy you can extract, the more capacity you can extract. And so with a transcritical system, we can extract anywhere from 40% to 70% more heat per unit and per unit of power than we could with a subcritical type system, which is really, really amazing. And that's the fundamentals behind why CO2 heat pumps can do so well. So next, I really want to talk about different multiple modes of operation we could put a heat pump into. First one is cooling only. Think of chillers. Think of water cooling systems and air cooling systems. Think of heating only. Think of boiler replacements, condensing boilers, heating heat pumps, domestic hot water heating, etc. But what's really unique with the heat pumps we've designed that are very unique in the marketplace right now is they utilize a truly simultaneous heating and cooling loop, meaning we can extract heating and cooling at the exact same time in the same unit, in the same circuit. There is no reversing valve like most subcritical HFC, HFO type synthetic refrigerants have. And I'll get into that in the follow-up slides. Operational range right now is huge. We're going from 0 degrees to 120 degrees right out of the gate. Normal heat pumps that are on the market that you can buy commercially today are rated by a AHRI standard. It's 550, 590. That's the way the energy code's written, and they classify all the variables for heat pumps. So with this, the systems we're designing today have an operational cooling range from 30-degree water systems all the way up to 75-degree water. And on the heating side, we can heat up water from 90 degrees all the way to 180 degrees. We use variable refrigerant flow for high stability of all those loads, and we can operate them independently. Now, domestic hot water heating is definitely new and a novel case for CO2 as a refrigerant. And there are a few companies that are coming on board with this now. Any domestic hot water heating system really needs a very high delta T to make everything work. And so you need that 100 to 150 degree delta T to make domestic hot water heating work, but it can do up to that 180 degree water. Most of them are about 140 degrees. Now, where Flow is one of the very few, if not the only competitor playing in the boilers, hot water boiler space, is at low delta T, less than 20 degrees. So for instance, 160 degree return water and 180 degree supply water. Now we're talking true direct, one-for-one hot water boiler replacements. Sure, we switch it to power, but there's things that we can do to really mitigate the need for additional power. So I want to show you a really basic schematic of how a CO2 heat pump system may look. So what you see here in the middle are compressors. We have a medium temp primary compressor, and we have a parallel flash gas compressor. You take that and you can heat the liquid up to 320 degrees if you want to. But this is not just any liquid, it's a supercritical fluid. And this supercritical fluid can have pressure, temperature, and enthalpy detached from itself, meaning that we can make it do some really interesting things, like 100% sensible heat extraction, or vary the pressures to optimize COPs over time. Every one of our units is set up with up to 2 heat exchangers. Now we can do things like run our hot water boilers on one circuit, and maybe a domestic hot water or air handling hot water heaters or in-floor heat or whatever else you might want to do, thermal energy storage. The possibilities with a system like this are truly amazing. And each one of these systems can be turned down to 0% modulation. So you can actually turn an individual set point and circuit off inside of the unit. If there's any heat left over, it goes to our gas cooler, and we either heat or absorb additional energy that way. Something new with the transcritical system is a pressure reducing valve. These take that gas that hasn't changed and condensed in the transcritical line and brings it back to a liquid. We do a phase separation in our receivers, so we recompress any vapors and put it right back into the system in the parallel compression stage. And then we get a great solid column of liquid to make a lot of cooling happen. It's direct expansion, DX refrigeration after that. And that's your standard chiller operations. What's really cool with a system like this, there is no reversing valve. And so you can turn a circuit on or off. You can do no cooling and only heating. Turn those heating circuits off at the right and just use this as a chiller. It's highly efficient and highly balanced. And when you do simultaneous loads, what really is a bane of any simultaneous load is uneven loads, where you don't have the same heating load as you do with cooling loads. We have a great benefit of adding an extra heating or cooling source to the outside ambient air with a system like this. And we can truly balance any complicated load profiles and make it a great option for any building. Now, for the energy nerd in me, I start looking at the power of a system like this. So usually we only have a single mode of operation device. So it's either cooling or it's heating. But because we can use the other side of this and we can come up with novel uses for it, let's say we're heating sidewalks in the winter, or we're doing preheat of our outside air on our DOAS units, or you're running your domestic hot water and building energy storage in the building. That's free energy. You have whatever use you want to use it for. So you're talking like overall net system COPs in the range of 7+ for a lot of these systems, which is darn cool. You can do a lot with that. And I love to get my mind going. I have so many great conversations with engineers about this. So getting a little deeper onto that pressure enthalpy diagram, what's really neat is you can extract high-grade heat and you can extract low-grade heat out of the same system. If you don't need that low-grade heat, you adjust your gas cooler temperature. If you need more, you adjust your gas cooler temperature. If you want to be more efficient, you lower your pressure. So you can move this top end all over the place while still holding this bottom end in the chiller constant, which is pretty neat. If anybody wants to talk more about the real nerdy stuff, I'm always happy to talk about that. Now, we've set up our systems so that they are modular and standard sizes, and they're split. So that way we can do as many possibilities as possible. I mean, we offer nominal sizes in the 30, 60, 90, and 120 ton ranges. They consist of either an interior or an exterior unit, basically the same piece of equipment, just with cladding or not indoors. And then you get a choice of a gas cooler. You get a small footprint V-bank gas cooler. You get a low profile for those sightline projects we want to do to get below some kind of screening wall or something like that with our horizontal gas coolers. And we have vertical gas coolers that are really great for things like parking garages and industrial applications, where you have high ventilation, where you want to pump through your gas cooler and take advantage of some unique environment like 60-degree year-round temperature in parking garages. So the possibilities are really, really amazing with a system like this. Now we can set these up as either water to water or air to water heat pumps. So there's some pros and cons to doing it both ways. Air to water, we can do a lot of that uneven load balancing, and they're really simple. These can be packaged all together on a single base rail and shipped as a unitized piece of equipment. And it minimizes anything for a tech to do. They hook up water and they hook up power, and you're off to the races. Or we can do it as a water to water, as a heat recovery or a booster application, and do a lot of really cool load leveling applications, or a mixture of both of these. Now, how are we doing on time? I see a couple things in chat, so I want to pause for a moment. Do we have questions right now?
I haven't seen any new questions come in. We're doing well on time.
Great. Oh, sorry. All right, getting back to it. So doing some comparisons, just to give a really high level comparison on pricing and how a building may be laid out. That always comes up, so we definitely should address it. So we're on the left side, we're talking about existing buildings. They consist of chillers, furnaces, and boilers. Now that's our baseline to go against. What a lot of people are doing on these heat pumps, because we have limits on that maximum temperature that we can do, and the way we handle defrost in those systems, because of that reversing valve, we have to always size a redundant module to keep heating on when we go into cooling, because they flip the thing into cooling mode and it's cooling down our inside space, where we don't want to do that. So we always have to design a redundant defrost module. Now there's a lot of new equipment and it gets really complicated. So looking at that with a system like I showed you everyone here earlier, is now a heat pump here that can operate cooling and heating at the same time, if it's planned that way, can take roughly 50% the overall footprint. And we've seen this with multiple studies that we've done in the last year. And sometimes it's as much as 50% reduction in overall footprint. It's competitive on pricing, if not a little bit cheaper, by about 10 to 12% in some cases. And it really fits the bill, especially with a split system to hide it all over a campus or a building, especially when you're doing retrofits. Now, when you're doing a retrofit, that's a whole nother story, because now let's take an existing office space with, let's say 200 VAV units, all designed to operate at 180 degree supply water temperature. No heat pump can do that. So let's say we change the heat pumps out and they can do 120 degrees. Now at this point, you have 200 VAV boxes in a finished premium space where you got to rip out all the walls, all the ceilings, and change 200 boxes, as well as buy all new heat pumps. And your entire building water loop needs to be upsized to account for that pressure difference and the temperature difference. That is a very expensive proposition. A system like this that can actually be a one-to-one application with a boiler, and it can replace a chiller, can allow you to not have that huge expense of redoing the entire inside of your building. And you just keep using your existing equipment, and maybe just put an outdoor air unit in a parking lot, do a changeover piping, and change it over in a week or a weekend if you're really on top of your game. Now that's pretty amazing. But the next part about that that's even better, because you can do simultaneous heating and cooling on a one device, or either or heating and cooling, is you can combine operations. So a lot of times in this electrification and decarbonization movement, we have a problem with not having enough power. Even in new construction, there's not enough utility coming to a lot of these sites, but there is enough to run a chiller. So if you substitute that chiller out with a new CO2 chiller that can also do heating, now you have the exact same power utilization, because they are equivalenting overall efficiency and capacity. You don't have to bring in new feeds. You can get rid of that boiler as needed, or change it out and leave it in place as a backup, for instance, and make two different heating sources, one for your low temperature hydronics or your domestic hot water heating, and another for your boiler modes or your in-floor heat, or whatever your system might want to do. And that makes some of these retrofits just simply amazing. And so payback is almost immediate in those cases. I want to talk a little bit about COPs, and basically this is our efficiencies. So the first thing is I've heard CO2 is less efficient in cooling mode. It's not. It's about equivalent to same as a 410A system. Our dotted red lines is our 410A heat pumps. Our blue line is our flow CO2 heat pumps. The dotted green line you see here is an adiabatic misting system. Basically a little spray nozzle misting your coils with a little bit of water. Now, if we mist the equipment, it's actually more efficient than a traditional HFC system. And if you don't mist it, it's about the same, especially when you're looking at the IPLV, because they heavily weight these low ambience part load operations. And now on the heating side, because of that transcritical nature I showed you earlier, that system is anywhere from 20 to 40% more efficient on heating. Plus it has a lot bigger application envelope, where many systems, they have to start either they turn off at 20 degrees or they start injecting liquid at 20 degrees into their suction gas to really artificially raise that suction temperature in order to make it work longer. That seriously takes away from your capacity. And when you take away from your capacity and still the same power, your COP drops like a rock. Now looking at a simultaneous mode, anywhere that's that 50 to 70 degree window you see in the middle on the left here, open a window. That's your economizer mode. We really should just bring in some fresh air and make everybody happy. But outside of that mode, look at how much more our blue lines and our dotted green lines are than a traditional dotted red line HFC system. You can really take into account really high temperatures and low temperatures and maximize your efficiencies across the board. Looking at capacity is a whole nother thing too, because what I'm showing here is a nominal 50-ton unit. You size it for 50 tons at 95 degree outdoor air temperature and get your capacity there. But if you look, let's keep that 50-ton line going, or 60-ton line going, depending on how the compressors are laid out. The COP or the CO2 heat pump holds on at or above the rating condition all throughout the application range, versus you see how as you get hotter and as you get colder, the 410A heat pump just falls apart on overall capacity. And that's where you have to start injecting additional things, and why anything below 20 degrees is the recommendation to use electric resistance heating or electric boiler backups. And that's really because the refrigerant has limitations there. Now, since, as you mentioned earlier, having a lot of practical experience under our belt, I've worked on cars, I've worked on heat pumps, I've worked on air conditioners, furnaces. I have pictures of me dangling by my feet out of air handlers in the middle of New York City, upside down in a 5-story high rise. You want to be made for service. Everybody's going to be a lot happier for you when you have that. And so that's very much in our mind. So everything has very easy access. It's all reach and access from an arm's length. All parts are serviceable. And a lot of times these are mission critical loads, especially in heating modes, where they can't go down. You can't turn off your heat in the middle of winter to do some basic maintenance and service. So all the critical components have isolation around them so that you can turn it off, service it, and put it back into service without shutting the primary system down. So as long as you're doing preventative maintenance type items, the system can 100% stay running. Another interesting thing with CO2 is the pressure is higher by about a factor of 3 than 410A. So we're talking maybe 1600 PSI to 1700 PSI on the highest side of the transcritical system. No tech really wants to put on gauges at that because their gauges might be only rated to 800 PSI. So with that, we incorporate gauges and pressure transducers going right to the controller right there. So the only time we really need to do anything with them is on initial calibration on startup. After that point, you have at least 2 points of reference to make sure your high side is always under control. Your low side has all that too. So it's really actually kind of fun to service these pieces of equipment. You don't have to go and hook up your gauges all the time. You can literally just look at the controller. It'll tell you what's going on. And this is all reported over the network too for our fun energy modeling people that just grab the data and go. Now, the receivers also have built-in site classes, so a lot of times you can't tell if a system's low on charge or not, especially in transcritical. So we put built-in indicators on all those items. And then we are using all stainless steel fittings to make all this work. So a lot of time, most systems are done with copper. Copper is a very ductile material, where in the fact that you can get a lot of pinhole leaks, it's very sensitive to acid and corrosion, and it can flex and break really easily. Stainless steel, on the other hand, is a lot more resistant to all of that. We weld all of our joints and seams inside of our rack and our heat pump so that it doesn't have that occur. And on the whole, from all the installations I've seen, I've probably done 30 myself, and my partner's done well over 100. They are dramatically better than any copper system you may see. Controls are very simple, very easy. It is different, so because of that, we like to bring all that right to the front of the controller so people can see it and monitor those points. We partnered with Corel to make all this work really exceptionally well. They've been at it for 30 years on the transcritical developments. That is a long time. They're one of the first ones to get into any kind of transcritical CO2 operations. And they've been exceptionally helpful every step of the way. And they have the most installations of CO2 components in the world. Now I want to highlight a little bit the split systems. So I mentioned we can package these on a rail, that they're a common unit. You could drop it in and you're done. No high pressure piping to worry about. Hook up your water with a couple of Victaulic connections, hook up your electrical load and go. But there's also the possibility of separating these systems for those tight environments where you want your heat pump inside your mechanical room. You want your gas cooler up on your roof behind a site wall next to your dumpsters, on top of your garage ventilation exhaust, something fun like that. And with a system like this, it's very possible. Right out of the gate, they are set up to run 100 feet and up to 50 feet of elevation change. Our record holder, done by our CEO personally, has gone 1,000 feet and about 200 feet of elevation change. He's quite proud of himself on that installation. So but it's the power of CO2 as a refrigerant that can do that. It's volumetrically much more efficient than any other refrigerant out there. And because we are guaranteeing a solid column of liquid, we can do things like this, which is really cool. The pipes can get hot though, and we're talking discharge temperatures between 200 degrees to 300 degrees. So you are going to want to insulate those lines just from a fact of nobody's bumping their head and instantly branding themselves with something fun. Or I think the Seattle Energy Code also dictates that we should insulate with a minimum of 1/2 inch to 1 inch copper on any refrigerant line, regardless of what it is. So it's a really nice thing for safety, but it's not necessarily required for efficiency. Now I want to highlight installation and maintenance a little bit. So on an initial startup, it is really important that we pull a good vacuum. All the great things you would do for any refrigerant system, you really should do here. It's still a refrigerant. We want to make sure we use refrigerant grade CO2, none of this beverage grade CO2, because it has little droplets of moisture in it that becomes a problem. But once we get that out of the way, it's really checking the oil and adjusting. It's charging. It's making sure you're calibrated on your first bit. And that's where our companies and our service partners help us out quite a bit. And clean out the strainers and any debris. We put strainers on everything because I've never seen a system show up that was clean after all the contractors get done with it. So we make sure that that comes in no matter what. After we get past all that point and pulling shoes out of your strainers and leftover tools, these things are industrial grade, for lack of a better word, meaning that they can go a prolonged period. And with the receivers and our oil management systems, active oil management systems that are included in here, they can handle the shoulder seasons like a dream versus a lot of critically charged, very tight HFC systems. You're always going in and adding 5 pounds of refrigerant here, trimming it out there, adjusting the superheat there. There's a lot of touch points on a system like that. You won't see those same kind of touch points on a system like this. And again, we want to make sure we check for any debris, make sure the coils are clean on the gas cooler, make sure there's no unusual faults, although your controller will be reporting into the BMS and alarming as we go. And again, flush those strainers because who knows what they found in there. I once found a dead pigeon inside one. That was an interesting find. Now, there's another element. I mentioned this high pressure that a CO2 can run. But really what's unique about it, it doesn't make a jet of laser cutting CO2 gas. It makes a small crack and it leaks. And then it rapidly expands and it makes dry ice, which closes it off partway. And you got a built-in leak detector coming out of it on the other side. So you get this nice ball of clean white frost coming out of your system so you know right where your leak is, which makes it awesome for troubleshooting.
Sean, we do have a question in the chat asking if your equipment meets the Buy American requirements.
Yeah, that's a great question. Thank you. And so the way our manufacturing happens right now, about 50% of it is done in South Africa. That's the sheet metal, the stainless steel piping, and integrating the high pressure circuits. All electrical. Most of the components have been manufactured in the United States that we've sourced, except for a very few. But I would say 70% of the components are manufactured in the United States. And then all the controls, all the electrical, and all the final test and assembly and quality control is done in the United States and Minnesota, which means we are well over the 55% threshold for Made in America qualifications. I think it comes out to about like 70% on average for most units. We are, in the next few years, we're looking to add in a R&D center and a prototyping and fabrication facilities here as we continue to grow and do more. But as of right now, I believe we qualify. And we'll get that certified and all the necessary arrangements as this comes through this summer. Does that answer the question for who asked it?
Yes, thank you.
Excellent. You're welcome. So we talked a little bit about PFAS. I'm not going to go back in there. But I would like to dive in a little bit more on the environmental sustainability portion of this. And so I love this chart here on the left in that it shows a gas boiler and an HFC chiller on the annual metric tons of CO2 emissions. Immediately, heat pumps blow it out of the water. It's a huge reduction. But there's still all those high GWP gases and leakage rate you got to deal with of that. As I mentioned earlier, the leakage rate is about 20% a year as reported by the EPA on most systems. VRF with 10,000 fittings and a little bit more. I've yet to meet a VRF system that doesn't leak profusely over time and drive everybody nuts for the first couple of years to figure it all out. So that number could be higher. So when you take that into account and eliminate that GWP and make that high performance heat, we can now drop that another 40 times on our total annual metric tons of CO2 emissions, which is just for the people who care about that, that is huge. Now add in some other benefits, like we are using adiabatic cooling. We don't have to, but when we want to get that extra bit of efficiency out of a system, adiabatic cooling is about 70% less water usage than any cooling tower out there in the market, which is really awesome. There are adiabatic cooling towers, but if you're going to change that out now too, why not use the right system? It is a future-proof refrigerant. It's a baseline in which most refrigerants are judged against. I showed you that earlier. And it really has no PFAS to be heard of. So it's a really great non-toxic environmental case. So to sum it all up, we're looking at a heat pump that has technology with over 80,000 installations across the world, just unfortunately not here. And it uses existing technology and components. I mean, the first one with all of these devices I can remember, as I mentioned, was 12 years ago in California. I have some friends who've done earlier than that up in Montreal. These are economical solutions. You can find the components in distribution houses. There are compressors in stock. It's not all the CO2 compressors for one company in the world. Bitzer are made in Atlanta, Georgia. Doran is the other major CO2 compressor manufacturer. They have facilities in Tecumseh, Michigan. They're putting in a plant right now, expected to be online by the end of the year, where they're going to be making the bulk of their CO2 compressors. So the United States is becoming the hub for CO2 components. You have people like Parker Hannafin and so on that exist in Missouri, and our market is just itching for somebody to step forward and start using all the great stuff they're building for the rest of the world. Now, it really is the right choice for a refrigerant, as I showed you. It's a natural, non-toxic, non-flammable, and it meets all codes and requirements. And we really do have one of the very first low delta T boiler level heat pump replacements on the market. We have patented simultaneous heating and cooling technologies in here. And with that, we also have a lot of defrost prevention. I didn't get into that very much because it gets into some technical discussions. Basically, we're making preheaters for the outdoor space to offset by about 5 to 10 degrees the need for defrost. And overall, we have some of the highest efficient and most efficient COPs in the market. Your centrifugal chillers will outperform this. We are using reciprocating compressors. There's just fundamental issues there. But we have a lot more resiliency and a lot more adaptability with a reciprocating compressor than we do for a centrifugal. So I would argue that like for like, they go pretty toe to toe. To give you an idea on where these things are made. So this is a image of our plant in South Africa. They have almost 200,000 square feet. They are firm believers in discipline and ISO and making a great quality product. Everything's 3D modeled. They actually were once a Gutner plant back before apartheid happened, and then they took off and became their own entity to really shine. And so it's an absolute pleasure to work with them. Plus, if anybody wants, we can go on an African safari and go see some lions and giraffes while we're at it. Quality is of utmost importance to all of us, where they still have an apprenticeship program with all people on the floor where they have to learn and grow and adapt into their trade, which is really fun to see. And their weld qualities and all their quality procedures are top notch. And that's where I have some information for today. So I'd like to open it up for questions and discussions or any follow-ups from anybody.
That was a lot of information, I think, for everybody to sort of process, for sure. But if you have questions, you can pop them in the chat. You can also raise your hand if you'd like to ask one. I see one come through. What's the larger facility you've seen retrofitted with a decent ROI? How many modules did it require, and the coldest area?
Well, we're working on one in Toronto right now. They have a design temperature of 0 degrees. And while I don't think it's going to go that way, the maximum potential is 85 units. I mean, it's a full district heating and cooling plant. I would say 500 to 1,000 tons is a very nice ROI point. And you can go up to maybe 4,000 tons for the top end. Our modules are anywhere from 100 to 140 tons for our largest size. So you don't want to go too many, but you also don't want to go too few. That answer the question?
Yeah, actually, the Toronto project is actually my project.
Perfect.
And the ROI is terrible, which I guess is why I was asking what, like, is the sweet spot or the highest range. is.
I would love to talk to you about that. So
It's not the ideal setup, but yeah.
no,
yeah, we
it's
can take a look at it.
that one's a tricky one. So
Yeah, I know.
but I know with some of the original stuff we talked on that one, we wanted to scale it back down. So it's about 500 to 1,000 tons is where it really starts to make sense.
Yeah, that's helpful.
But you got to watch your return temperature is the absolute best thing to do to increase your capacity and your efficiency. So if we drop that return temperature down, that's going to really help. But yeah, send me a message. Let's talk about that one more.
I'm curious.